One thing to, so I'm going to plan to at least start every class period, pardon me, on Zoom like this. And this link will keep you working. It'll be the same link each time. But at the very least, then I can sort of introduce it to you, and then we'll go from there. Also, since I didn't give you a chance, because I had just printed off the homework packets and the syllabus, so I haven't given it to you yet. And so we're going to do homework differently, chapter, at least as long as we're virtual like this. And what's going to happen is, instead of me giving you a syllabus in a big packet, since I can't do that, every day I'll give you a daily assignment. And like today, the plan would be that you should be able to finish it before you leave. And that'll be generally what I'm going to try and do. I can't promise that that there won't ever be anything that you have to finish outside of class time, but I'm going to try and make it so that to help keep you organized, I'm going to try and keep it all within class time. We've also been asked to limit the amount of homework we're giving you anyway. So so that's kind of how I'm planning to do that. I'll also just point out here at the bottom, so like I said, instead of the syllabus today, you'll make sure to do the daily assignment. But also, if you would like to do corrections on your last test, so that is open now, and you can start corrections on this. I think that everyone who's on has taken it. Am I right about that? Sam Torres, maybe not. Sam, I'm going to send you an email later, because obviously you're not going to be able to come back to school to take it. So I've got a plan, but I'll send you an email about that separately later. All right. So go ahead and get out something you can take notes on. And today you can label your notes uniform circular motion. All right, so when we talk about uniform circular motion, so this has a lot of applications, and we're going to talk about all of them in this unit. The first thing that might come to mind is like satellite motion. So if you talk about satellites that orbit the Earth, or like natural satellites like the moon orbiting the Earth or the Earth orbiting on, that's going to be an example of circular motion. But circular motion has several more terrestrial applications too. For example, I mean, roller coasters, if you're going in a loop on a roller coaster, that's a circle. And so if we can understand circular motion, we can analyze that. The other thing is, even in the car, if you are going around a corner in a car, even just like making a left turn, right? A left turn is nothing more than a quarter of a circle. So understanding circular motion opens us up to talk about a lot of things. My plan had been that we were going to start today with a lab that we can't do now, but this is the flying pig lab that I like to start circular motion out. So I just want to show you what I've got here to kind of introduce this. So I've got this toy pig hanging from the ceiling, and we were going to do some measurements with this, but I'm going to set it up going in a circle. So the idea here is you got to think about, what did you need in order to make this happen, right? So what we've got is we've got a string attached to a fixed center. So that's an important thing to have. We have to have a string attached to a fixed center. And then we have to have something keeping its forward motion going, right? And so this actually ends up being, let me stop it here. This actually ends up being a good way to start thinking about circular motion, because it talks about the two ingredients that you always have to have circular motion. And oops. And those two ingredients are, first of all, you have to have forward motion. In my flying pig, that's what the wings are for, because the wings here, they're not providing any lift, right? It's not, the wings aren't actually causing it to fly. But if you were here, we were going to do this experiment. You were going to be able to tell the wings, the point of the wings are they push air backwards. And so the wings are what continue the forward motion of the pig. And then the second thing that you need is a force directed towards a fixed center. And we call this a centripetal force. So if you think about it, circular motion is just a fight between these two things. And if they're in perfect balance, you get a circle, right? Because you have something that wants to go forward, but in this case, like the pig, it has some forward motion, but it's attached to that string. So instead of going forward, it has to turn, right? But you got to have both those things. You got to have that forward motion, and you have to have something pulling it back towards the center. I'm going to draw this real quick. So the idea is, if you have an object, and I'm just going to draw this object like going around in a circle like this. So the velocity, you can tell, is always changing directions, but it's doing that because you always have this force pointing towards the center that we're going to call the centripetal force. FC for force centripetal. Couple fun facts that are good to note. First of all, you'll notice these two vectors are perpendicular to each other, okay? Because if you remember from geometry, a tangent line is always perpendicular to a radius. And so the velocity is a tangent line, and the centripetal force points along the radius. So centripetal force and velocity should always be perpendicular to each other. And so that's interesting because you can think about forces now. Remember, forces cause accelerations, and there are three ways to accelerate. You can speed up, you can slow down, and you can change directions. So if you think about it, right, the type of force you need to speed up is you need a force that pushes you forward, right? If you want to slow down, you need a force that pushes you backward. Now, if you want to change directions, you need a force that's perpendicular, right? Okay, so those are the ingredients of circular motion. Now I'm going to give you a couple equations that go with this. So the first of all, the equation for centripetal force, and sometimes it's a combination of forces that cause a centripetal force. So we're actually going to write it as the centripetal net force is equal to mass times the centripetal acceleration. And acceleration is going to be equal to v squared over r. So this first equation should make sense to you because that's just Newton's second law, just written with a c in it. This equation, for the sake of time, I'm not going to derive it for you. If you like geometry and you like mathematical derivations, I have posted a recording on Schoology, and I'll walk you through how to get that. But for now, I'll just have you trust me that that's the formula for centripetal acceleration. And then the other thing we're going to do is we're going to do the velocity of an object that's going in a circle. And the velocity is going to be equal to 2 pi r divided by capital T. Now, this equation should make sense because velocity is distance divided by time, but what's the distance around a circle? The distance around a circle is called a circumference. So it's 2 pi r divided by capital T, and capital T is going to be this symbol that stands for what's called the period, which is the time of one rotation. Is what we mean by capital T. All right. So those are the questions. Before I go on, anyone got any questions to ask at this point? All right. In that case, let me pull up a video that I want to show you. Share. Okay, so you've probably seen one of these before at the museum or whatever, where you put the pennies and they go in a circle, right? So the idea here, what you've got going on here is you've got that funnel, and the normal force on that funnel sort of tends to push those pennies to the center, right? And so the normal force in this case is what's providing our centripetal force. So the idea is you have a centripetal force, but you have to have both things. You have to have centripetal force and you have to have forward motion in order to keep going in a circle. You'll notice here early on, there's a point where the two pennies hit each other. So right there, right? When the two pennies hit each other, they no longer have any forward motion. And so if they don't have forward motion, they're just going to have a centripetal force, right? So if I go back to the drawing that we had, I go back to this drawing, you can see here, right? If all of a sudden I lose my forward motion, the only influence I have is my centripetal force. I'm going to go to the center, right? You can also see this with, I had a demo here that I have misplaced. Oh, there it is. Okay, so you could also see this, the opposite happens here, right? So what I've got here is I've got a piece of tape tied, or a roll of tape tied to a string. And right now that tape has forward motion and it's got a centripetal force that this time is being provided by the tension in the string, right? And if all of a sudden I let go, right, what did it do? Probably couldn't see that, but the idea is it's going, if I don't have a centripetal force anymore, right, all I have is forward motion, and it's just going to go whatever direction it was going before I let it go. So I have to have both centripetal force and forward motion in order to have a circle. If I lose forward motion, I just go to the center. If I lose centripetal force, I just go in a straight line. Okay. Questions about that? All right. One more thing I want to show you here. This is a lot cooler when you're actually here and you can see it. But what I have here is I have a bucket that's got some water in the bottom of it. I don't know if you can see that, but you're just going to have to trust me. There's some water in this, the bottom of this. And what I'm going to do is I should be able to, well, if I don't hit anything, I should be able to make this go in a circle without losing any of the water. So there we go. I hit the pig. I wasn't paying any attention. Well, anyway, where did it go? All right. Well, okay. So anyway, here's the deal, right? So you can actually do this, and colloquially, sometimes people will refer to this as centrifugal force that like pushes to the outside, but that's not actually what's happening here, right? So I want to talk about what actually is happening here. So let's go back to the notes here. So there's something, and you can feel this. You feel this too, like if you're on a roller coaster and you go around a loop, you know how you kind of feel like pushed back into your seats? what is it that's pushing the things to the outside of the circle? It doesn't look like there's any force in this picture pushing things out to the outside of the circle. Why do they feel like they go to the outside of the circle? Anyone have any thoughts they might want to share in the chat? Why does the water stay in the bucket? Why is the water, quote unquote, pushed to the outside of the bucket instead of falling out of it? A lot of times people say, well, maybe it's the centripetal force, but look at where the centripetal force points, right? The centripetal force points towards the center. So if that were the case, right, I would be pulling the water right out of the bucket. Yeah, so Sam's got it right here, right? The velocity of the bucket and the water acting on each other. So that's part of it. And the other part is, what does the water naturally want to do? You think about the first law, right? Object in motion wants to stay in motion. The water, so at this point in the bucket's going like this. At this point in the motion, the water wants to keep going that way. It's got inertia, it wants to keep going that way. But what happens? Well, the water tries to go this way, but then the bucket gets in its way, right? So a moment later, the bucket's right here. So now where does the water want to go? Now the water wants to go this way, right? But then a moment later, the bucket's right here, right? So the idea is the bucket always stays in front of the water, but it's the inertia that keeps the water wanting to go in a straight line, that makes it feel like it's being pushed to the outside. This is also how like a clothes dryer works, right? A clothes dryer, you know, has a spin cycle. And if you look in a clothes dryer, it's got like a little drain around the outside of the barrel. And what it's doing is it's spinning the water off the clothes. But that's a misleading way to put it. It's not actually that it's spinning the water off the clothes. It's that the water goes straight, but the sides of the barrel prevent the clothes from following what their inertia wants to make them do, right? The inertia wants them to keep going straight as well, but the barrel sort of prevents that from happening. So it lets the water go straight off of it like you'd expect, but the clothes do not. So that's how a clothes dryer works. All right. Any other questions here? All right. Here's what I'm going to ask you to do before you leave. If you go to Schoology, let me show you here. Can you still see that? If you go to Schoology, there's this day 36 assignment posted today. It's probably also on the timeline. What I've done, like I said, instead of giving you the full syllabus, I'm going to cut it into bite-sized pieces. And so I put these 3 problems here. And what I'd like you to do before you leave is I'd like you to answer these on a separate sheet of paper, and then just take a picture of it like you would a normal homework assignment and upload it here. Why don't I kind of think maybe I'll stay on here, and you can stay on here too to answer any questions you've got. But just go ahead and work on these 3 problems, 1, 2, and 5. I've got the answers so that you can check them here. As soon as you finish them, you can upload them onto Schoology, and then you are done for the day after that. Any questions? All right.